Well, you were supposed to use this data twice. The second time to remove the 3 circle observations and reanalyze the data in that unbalanced case then. I didn't grade the second thing, okay? Although I noticed one thing kind of funny on a number of the papers on that second one. The total number of observations that we have here is 18. So we should have 17 degrees of freedom for total. Okay. Now if you take away those 3 observations, now the total should have 14 degrees of freedom, right? A lot of people did the second problem that had 17 degrees of freedom on total. So I don't know what you did. I couldn't really tell what computer commands you were using. But anyway, that got sort of twisted up on the second problem anyway. But anyway, I wasn't grading that second version of the question. There was enough to deal with the first part of it. So let's see. What should I talk about here? Oh, the first thing I should say is that a number of people saw nesting in this problem. There's no nesting here. So we have factor A might be this nitrogen on the top, and it has 2 levels, and then factor B would be this time period, early, optimum, and late. And so there was the thought that somehow factor B was nested in factor A. That's not the case here. Factor B just sits there as it is. It's not nested in any real way with factor A. So if you started off with thinking this was a nested problem, everything goes astray right away at the beginning because you get the wrong terms in the analysis of variance table, you're doing the wrong test, and everything is all tangled up. So that was unfortunate to make that judgment already at the beginning that somehow this was a nested problem. So this was not nested, it's just a cross. So what I did was to set up some columns in Minitab like this, where factor A was the top variable. What was it called again? The nitrogen inhibitor. And factor B was the next level down, the time period, 1, 2, 3 levels there. And then there were 3 blocks for the 3 rows, so I have a block column here, and then here's the response Y that I have here. So I just set up a model where I have the response is a block variable, and then there's factor A here, factor B there, and then the A by B interaction term there, and that's all. I made the blocks random, as is usually the case. And then I got the typical output that comes here, which is easy enough to interpret once you get it. Yes.
Why block was random?
Pardon?
Why block was random?
Blocks are almost always random. There's hardly any example where they're not random. Because blocks just our turf that we're using for the experiment, and we selected from available turf.
But
What-
when we did one example in class, we assumed that block was fixed. When we do a randomized block, complete block.
Yeah.
We assume that random was, that block was fixed.
It's probably true that that happened in an example or two. You see, they don't really tell us much about the blocks in a problem like this. They don't really say what's going on with these blocks, other than that there were sort of like 3 repetitions of the experiment. And so that's the way I interpreted it. If there's like 3 repetitions of an experiment, then these quote blocks that we have are, to me, random. They're not fixed in any way. I don't have any particular interest in these blocks as a factor that I want to say something about. So I take it to be random in that instance. That's not a great explanation, but I tried it the best I can.
One more
Yes.
question, please. And why you didn't incorporate the interaction in the ANOVA table, the interaction between block and the other factors?
Well, I guess that's more or less my style, and I think most of the sources and books that I read omit those kind of terms as well. So you say, for example, I could have included in this model some interactions, A with blocks, B with blocks, and so forth, and I didn't do that. I just left block as a single factor in the model. And that's more typical of how we handle blocks. It's hardly a matter of being, what should I say, right or wrong. That's a little too strong. But typically they don't want to study anything about interactions of factors with these blocks.
Yeah, but at the beginning of the semester, you also taught us that if we analyze interaction, we can reduce the error of the model using the interaction between the block and the other factors.
If I add those terms into the model, I do what? I reduce the
Error, the MSE.
I reduce the MSE. That's probably true. But another thing that happens is I also reduce degrees of freedom. So it's like 2 forces are working against each other. It's good to reduce the MSE. Then tests are more likely to be significant. But then I'm reducing degrees of freedom as well, and that's going to change the critical value that I'm looking up in the F table. And so those 2 forces work against each other. And it's hard to say which is the dominant force. It might change from one data set to another as to which is the dominant effect. That's not fair that you remember what I taught you a month ago.
I like it,
I'm not sure I remember what I was saying a month ago. Okay, so anyway, I think that's the key with solving the problem anyway. To set up the model that way, with block standing alone. And I might just point ahead to something we talked about last time. This is the split plot experiment handout, and we'll continue talking about that today. But the model that's given here has a block effect, which is just a single term in the model. We don't worry about the interactions. Well, I guess I'm saying that wrong. Here in this model, I guess we do worry about the interaction of that block effect. Forget that comment. That's taking me astray. Then I reran the data, omitting the 3 observations. what I noticed in the second run is that the total now has 14 degrees of freedom for error, whereas it started off with 17 degrees of freedom with the original data. In fact, I don't know what some people were doing, but I saw papers where this was still 17 and the mean square error was 500 and something. Like way out of the ballpark. I don't know what in the world was happening there. So I couldn't really trace it down, so I just kind of skipped grading that problem. Okay, then there were a few side questions yet going on here. We were supposed to specify a model, so I said over here, let's let A be the nitrogen factor on top, B be the time variable, and then C be the block, and I took block to be random here, and again, we talked about that a moment ago. So the terms in the model would look like this: A, B interaction, and then the block effect is just a single term. So that's the model I used and when I entered into the Minitab command line as well. Now it asked for some standard errors for means, and so on the top variable nitrogen, we have to consider the mean of all the nitrogen, of all the data when the nitrogen is done, and then the other one is the mean of all the data when the nitrogen is this 0.5. And so those means are these numbers here. There were 9 observations in each group, and the standard error for a mean is the standard formula, the square root of mean square error over sample size, which would be 9. So I had to go back and find the mean square error. And I looked in the output, and the mean square error was 37.15. So I plugged that in there, and you get an answer, 2.03. Then when I want the means on the time variable, I'm looking at the data again, and I want the mean when the time variable is early, 6 observations there. The mean when the time variable is in the middle, 6 observations there. And finally, when the time variable is the last value, 6 observations there to take the average. So those 3 averages are these numbers here, 6 observations in each, and the standard error should be square root of the mean square error over 6. Because there's 6 numbers in each mean. And so that gives me an answer there as well. And then the last case was the individual cells. And for the individual cells, there's 3 observations in each cell. And I didn't even write down the means here on my paper because there's 6 of them. But the standard error would be the mean square error over 3. And that comes out to be 3.52. Well, anything more I should say about this problem? All right, let me put this aside then for now. I did the liquid last time. Here's my version of the handout. Let's see, that's a little too big. So in the split plot experiment, there's two factors. And we start by having whole plots. These are the big blocks here. And the whole plots are somehow divisible into smaller portions called the split plots. And so the way this is written out is that C is like replication or like block or something like that. But the nicer situation to think about for the meaning of this diagram and this graph here is to think about it as if this was an agricultural situation and we're talking about plots of land. So we might have farm 1, first replication. And in farm 1, we identify 3 whole plots of land. And we're going to do something on those 3 whole plots of land. We're going to change the value of a factor A at random. Notice this doesn't start equal 1, 2, 3. It's kind of mixed up because we assign the levels of factor A to these whole plots at random. And by the way, you can look down and say, in the second block, in the second farm, we have again 3 whole plots of land, and we're going to apply factor A to those whole plots. We do it in a different order than we did up here. A equal 1, A equal 3, A equal 2. The implication is that that decision is made at random. So, factor A might be, in an agricultural situation, it might be a type of fertilizer for the soil. So for this whole plot, we use this fertilizer. For this whole plot, we use that fertilizer. And for that whole plot, we use that fertilizer. So on this first farm anyway, we're getting data about the yield of this crop or some feature of the crop anyway on 3 different fertilizers. Now, there might be some second factor that comes into play, and it might be, for instance, type of seed. So if we're planting soybeans, it might be a variety of soybean seed, for example. And so what we've done in this plot of land is we've divided out 4 smaller pieces, and we're going to use a different seed in these subplots, and we make the assignment at random. So this doesn't go 1, 2, 3, 4. The assignment is made at random. Then we come over here to the second big plot, and we see it has subplots in it as well, and we're going to use factor B again in those 4 subplots, and again in a random order. So there's what came out here. And finally, we do the same thing in the third whole plot. We have these subplots in there where we're using a factor B. So that's the main experiment right there. And I call that replication 1 or block 1. I'm going to call it that. That's all right. And then we repeat that down here for a second farm or a second block. And we could have more as well. So this just stops at 2 blocks. But we could continue with 4 blocks as well. So this is the idea of a split plot experiment. You can physically sense that the land is divided up into whole plots, and then the whole plots are divided up into smaller parts, the split plots. And so this got what we call the split plot type experiment. Now basically, the point of this kind of experiment would be to study the 2 factors. What's the response as affected by factor A? What's the response as affected by factor B? What about interaction between factor A and B? Those are the questions that we want to answer with this experiment. So the handout goes on to say, well, how do we model the data? And there's the model equation. That's the standard one for a split plot design. So we have an A effect, a block effect, a interaction between A and block. We have a B effect, an AB interaction, and then the random error term in the model like that. So this is the typical model for the split plot design. There's a comment here that I mentioned last time, and I'll just repeat it again. Different books specify different models here, so this isn't the only model that's used in analyzing split plot data. It's maybe the most common one. But sometimes other terms are added in the model as well. So on the second page, here's an example. A is the level of nitrogen applied, B is years, C is blocks, 1 and 2, and Y is close. Or that's what was the meaning of the factors in the original source of this data. And I think I'm going to show you this data on a handout a little later today here yet. But I thought you could change this again, and I think it would make a better sounding example if A was the amount of nitrogen, B was the planting depth for the seeds, and then C was years. So anyway, here's the data. Here's the GLM command. And these are the terms in the model that you saw on the previous page. And I put them in a specific order here because I want the ANOVA table to come out in a certain order. And that's at the bottom of the page here. Now effectively they make a big deal in split plot experiments that there's 2 error terms in the model. And they often use that language directly. So I drew a line across the ANOVA table there to say the information above the line refers to whole plot information, factor A and factor C there. And below the line, the information is about the split plots. So there's an error term in the top, which is going to be the CA interaction. And so if you trace along these squares F, this mean square here for the CA interaction is the denominator that's used there and there. So if I take the 0.5 and divide it by 0.4, I get a little bigger as 1. If I take the 12 something divided by 0.4, I get 29. So you can kind of quickly see that for these F statistics over here, the denominator of the top 2 is this third line here. I'm not really interested in testing about this CA effect. C is blocks. I'm not really interested in saying how the blocks are affecting factor A. So this is usually just left and not done. But the importance of the CA line is that it serves to give me an error, some error mean square, with the other 2 factors that I'm especially interested in A. So then we drop down below the line where we have information about the split plot part of the data. We have factor B, A times B, and a line that's called error. Well, so if we roll along here, mean square error is this 0.2 here. Notice how that's used as the denominator there. If I take the 1.9 and divide it by 0.2, that's approximately 9. If I take the 0.69 and divide it by 0.2, I get the 3 something there. So these two F statistics are using this second here. I looked at the display of expected mean squares, and we've seen that for some rows we use this denominator, and for other rows we switch and use a different denominator. And we figure out which way it goes by having the expected mean square column as a guide. Well, in this split plot type experiment, when I read other sources and books discussing this, they don't usually have the expected mean square information available. They just say, hey, in split plot experiments, there's 2 errors, this one and this one, and just use them. Use this one for the whole plot, F statistics, and this one for the split plot, F statistics. And that's usually what you find stable. Now, what I have here in this output that I produced for Minitab is the table of expected mean squares here. And if you study these briefly, you can see that the denominator for B and AB would be this quote error term down here, 6. And for testing about A in particular, looking at its expected mean square, probably denominator would be this CA interaction from the piece we're seeing right there. So we can see in this sort of expected mean square view of things that we've been used to in other examples. We're getting the same kind of answer as the standard one in our split plot experiments. Yes.
Yes. Back in the analysis of variance table, remember in a true factor we check the interaction first. We test the interaction first.
Yep.
Do we do the same thing for the split plot?
Well, it sounds like a good idea, although I don't really see that comment made in the books. So as you're saying there, we should probably test about the AB interaction first. If we find there's no such interaction significant, then go on and test about main effect of A, main effect of B. That would be our recommendation from earlier, right?
Yes.
I don't see that kind of recommendation made in the books here in this split plot type experiment, but I think it's a good recommendation. So probably we should have began to test about the AB interaction and waited to see what the result was there before we looked at the other test. So let's go back and look and see what we're finding. Well, just barely, we're accepting H naught. No AB interaction. So if we go with that, then we could go on and test the main effect. There is an effect due to factor B, and there is an effect due to factor A, both highly significant. And I don't really care about testing for C, because that's just the blocks. I mean, that's not an element of the experiment that I care to make any conclusion about. This is the one I'm talking about right here. Typed handout as well. So this one comes from Poole's book. Here's the title, Analysis for Split Plot Designs. Here's a model equation which has a, let's see, how does it say it here? Rho K is a block effect. DIK is an interaction between A and block, which we had in our model. Beta J is a B effect. Alpha beta is an AB interaction, which we had in our model as well. So this model is the same one that I have in my notes. Okay. And here's kind of a summary table down here about which pieces in the ANOVA table we're going to be using. You can notice the language being used here in this source. This line isn't called the AC interaction, it's called error 1. And there it is, mean square error 1. And then down here, we have error 2, mean square error 2. So in this source anyway, those two mean squares are already called error mean squares. But there's two different error mean squares in this table. The problem is, perhaps seen more clearly, well, let me go back and finish this. So here's this handout. If you turn the page after some stuff, there's an example here about turf grass. And so there are 4 levels of factor A, this nitrogen source, and in this layout, it's over here on the left, rather than, I prefer it to be on the top, but we have to take whatever is given to us. The blocks are specified in here, and I don't like that layout either, but we have to take what's given for us. So we have block 1, which is that information, that information, that information, that information. And in block 1, we have all 4 levels of nitrogen being used. And the next factor, B, is this years of thatch accumulation, 2, 5, and 8. This is a little puzzling to me because this experiment is going to take 8 years to run. If they have to wait for 8 years of thatch accumulation of strip grass, that's a long time. So I don't know about the plan of this experiment, but that's factor B. There's no possibility of randomization in factor B because 2 years comes before 5 years, comes before 8 years. Can't change that, right? So you're stuck. There's no randomization on the application of factor B. But be that as it may, I thought when I first looked at this, that this was a nice set of data to look at, and it's in the section on the split plot experiment. So somehow we're supposed to view this as a split plot experiment. I find it a little strange to look at this as a split plot experiment, but I guess it fits if we push it a little bit. So factor A could be the 4 levels of nitrogen, and on those plots of land where the grass is grown, we're going to identify, I guess, 3 subplots in each whole plot, and then we're going to let the grass grow and tend it for 2 years in one of the subplots, for 5 years in another of the subplots, and for 8 years in the third subplot. So we could do that at random as far as which subplot was 2 years, which 5 years, which 8 years. That would be doable. But anyway, so in that way, I can see how this turf grass data fits this layout here. Well, the handout that I gave you after the data finishes with an ANOVA table, and I'm presuming that it's the same as in the class handout. Let's see here. Block 0.51, C 0.51. Nitrogen N 37.3, A 37.3. Air 1 1.16. There it is right there. And similarly, the other entries are going to agree. So anyway, the source of the analysis of this data gives me numbers that agree with the Minitab output that I produce also for the same data. Okay. So in these paragraphs that follow the ANOVA table, there's some comments that are useful enough. You can read them and make what you will of them. They're okay. And then that's it. All right, so there's this example about the nitrogen and the grass and so forth. Then I said, let me just try it out and see what happens. Let's add one more term to the model, because this issue of what term should be in the model is not universally agreed upon in the statistics books. So what I did was to take the model that we had and add to it a VC interaction term. And I don't know why, but I think I've seen that being done in a few other sources. So if I do that, what happens? So here's the new ANOVA table. You know, I know we do run into some troubles. It says there's an X, so it's not an exact F-test for factor A. So something got messed up. Let's look at the expected mean square column, which would come up next on the next page. So we're on page 4, we have the expected mean squares. And the denominators to use are, for testing the new term CV, we should use 7, the second error. To test AB, we should use 7. To test B, we should use, here's where there's a change. We should use this one here, the CV term. Now that's the new term that I added to the model. We didn't add this in the previous analysis of variance table, right? So this new one becomes the denominator for testing factor B. So that F is probably different than it was in the earlier ANOVA table. Then when we come up to the stuff in the whole plots, the top 3 lines here, we say, well, the CA interaction nicely is again the proper denominator for testing A. So that's matching up with testing A. But if I wanted to test C, nothing fits. Nothing in there is directly in these lines below. And so what they have to do is to cobble together a new pseudo-mean square and formula this for given right here in Minitab output. Okay, 3 plus 6 minus 7. And if you do that with these expressions up here, you get an expression which is a proper denominator then for testing factor C. Now, fortunately, I don't really care to test factor C. That's just the block factor, right? And I'm not really primarily interested in factor C at all. So I could just ignore that issue and not deal with it at all. And that's another probably personal thing, if this was an analysis that I was trying to run. I don't remember talking about this in the past. So here's example 2 on water use. So the description is down here below, I think well enough to understand what's happening here. We wanted to set up a split plot experiment to study the effect of 3 factors. Notice the change. 3 factors on the water use drip irrigation of sweet corn. 2 farms, those are the blocks, were selected at random. So notice we've set random blocks. And in each farm, 2 plots of land were chosen. 2 levels of phosphorus, labeled P1 and P2, were randomly assigned to the 2 plots on each farm. You can start to see that forming in the data layout above. So you see here's block 1. This is all for farm water. Block 2, that's all for farm 2. And at each farm we have, how did it say? We have 2 plots of land that were randomly seeded with phosphorus level 1 and phosphorus level 2. And so that would that farm. And then for the other farm, the same sort of thing. 2 plots of land, one got phosphorus 1, the other got phosphorus 2. And so that was going on. Now there's yet more going on here. It's described over here on the left. Now there's 2 variables over here on the left. Normally we've had just 1. So that's the fancy addition to this example. Normally this was factor A up there, phosphorus, P1. And this was factor B over here, the second factor. Now instead of a second factor, we have 2 factors over here. And so we need to see what happens. So these 2 factors are the level of nitrogen that could be used, 3 choices, and the watering that was used, 3 choices there as well. So what I saw in the description here as well is that these 2 factors together give me 9 different cases. 3 times 3 is 9. Okay. So what does it say down here below? It says each of the plots was divided into 9 subplots. So you see it coming. And the 9 treatment combinations on water and nitrogen were assigned to these subplots at random. So you have to visualize something like this on one of these plots of land. We've got to somehow divide it up into 9 subplots. And in those 9 subplots, we've got to assign these 2 factors here. And you should do it at random. So this doesn't say in row 1 you use water 15, in row 2 you use water 20, and in row 3 you use water 30. It doesn't say to do that. It says assign these 2 factors to those 9 subplots at random. So that's what's supposed to be done. So the easy way, putting 3 different waters in separate rows, and then the 3 different nitrogens in separate columns. The easy way is not the way to do it. We should mix it up. We're supposed to randomize where those 9 different cases end up in these 9 cells. So okay, suppose that was done. And now we get the data. Here it is. This is the water used by the corn plants. And so how are we going to analyze this data becomes the issue. Well, actually I'm going to cheat. So there's the data printed, and I should say here, emphasize to you that I'm going to form a new column that's 10W plus N. Now this is going to be, if you look at W, water is 1, 2, or 3. And then the N is 1, 2, or 3. So this is going to be, when W is 1, I'm going to get 10 plus 1, 10 plus 2, 10 plus 3. When W is 2, I'm going to get 20 plus 1, 20 plus 2, 20 plus 3. And then there's one more case when W is 3. So this is just an artificial way to generate a column with 9 different numbers in it. Okay, that's all I'm trying to do here. So I'm going to say this new column this is 11, this is 12, this is 13, this is 21, this is 22, this is 23, this is 31, 32, 33. I don't have to worry about the spread of those numbers, they just have to be different numbers, is all I'm trying to accomplish there. So one easy way to accomplish that in a computer program is to do some device like this. So what I'm basically trying to do is to say, this problem is hard because I've got 2 factors over here, and I only know how to analyze split plot data when there's 1 factor over here. So I'm going to make 1 factor over here, this treatment column. So that's my cheating on this solution. So then when I run this in Minitab, I do block. P is phosphorus, that's factor A. Then I do block by P. That's going to be the top error. Then I do this new variable, treatment, and then P times treatment there. So these last 2 entries in this model equation are just the same kind of thing that we've used before. There's 1 factor, treatment, this new one that I created, and then the original factor A was called P. I used random blocks again. I don't know why, Pedro. The farms were just probably picked at random from available land that we could use in the experiment. I have no particular interest in these 2 farms, so I treat it as a random factor. So anyway, I get the ANOVA table, and interpretation of this is pretty straightforward. We basically see that let's test the interaction first. So we look down below, and we try to test this interaction, and we look at the p-value. It's way bigger than 0.05, so we conclude not significant, no interaction. So then we go on to test for this new variable treatment right there, and its denominator is this error here, and it gives me a huge F statistic and a very significant F there. So the treatment variable is very significant. And now I leave that and go to the upper part of the table, the whole plot information, and I want to test about factor P, the phosphorus. And here's the P value. It's not significant, so I leave that there. There's a p-value that's rho for blocked by p. I'm not interested in that, so I can just ignore the conclusion from that p-value as well. Now, so there's how I analyze this data my first pass through. Now, the thing that's not good is that this variable treatment was highly significant, and it's a combination of two factors. So really, I should figure out some way to split that apart so that I can get separate tests about water and what was the other variable again? Yes. Now, I think with a little bit of trial and error, I could figure out a way to write this model line so that I could incorporate two variables instead of this one variable treatment here and get some kind of items in the NOVA table that I like. So I didn't attempt to do that here in this handout, but I'm just pointing it out to you as the next step. Somehow we should split apart this treatment variable that I created. It's highly significant. There are some significant differences going on there, and we should explore what they are. Okay, the rest of this finishes out the mini-cap output in the usual way as you've seen before. Okay. All right, that's a good place to stop then for today. I've got some more examples about split plots to talk about yet next class. We'll see how they go when we get there. Yes, the homework papers, bring up and leave on the desk here.